we are highlighting things, basic things you need to know, not going in depth, because in Ryan's flight controls class, you'll go a lot more depth into how flight controls work, types of flight controls. And I forget who teaches, I think Ryan teaches the helicopters class. So all the helicopter stuff, at the end of the chapter, we're going to skim through. You're going to have a whole class just on that later.
Why are we skimming?
Because you're going to have a whole class just on that, just for you too.
Thank you.
Later. So don't be hurt and offended. I'm skimming over it today. So by the end of lecture today, you should be able to demonstrate an understanding of the theory of flight. And I'll be pointing out specific things that you do need to know. So what is aerodynamics? It comes from some probably Greek words. Aero, so the first part of this word means air. How about that? And dynamics means motion. So in physics we talk a lot about motion. We already talked about motion, force, all that stuff. So aerodynamics is just the study of air in motion. And another concept you had to carry along with you today and in your understanding of aerodynamics is the viscosity of air. You're really going to talk a lot about viscosity when you get to lubrication class and hydraulics and the viscosity of oils and how in winter you want one type of viscosity and summer a different type, or else an oil that is magic that works for all temperatures, because it talks about stickiness or friction or the resistance to deformation at a given rate. So if you think about it as like the thickness or stickiness or friction, Jell-O is more viscous than water. Water flows easy. So just a simple way to think of it. And aerodynamics is a study of laws which have been proven to be the physical reasons why an airplane flies. We're going to talk about some aspects of aerodynamics that are still in deep discussion and debate among physicists today. So, don't worry. We're not going deep into aerodynamics, just introducing concepts. However, the concepts we do talk about, you do need to take seriously, because if you aren't doing repairs correctly to aircraft, taking into consideration aerodynamics and how air is supposed to flow, your pilot could crash and die. So it's very important to understand these concepts. So you don't have to be an aeronautical engineer, but you do need to understand surfaces have to be smooth. We'll talk more about that in sheet metal class when we talk about what types of rivets to use where. And in Ryan's flight control class, how you rig flight control, very important because of how the aerodynamics work. Alright, you might be familiar with the four forces of flight, and you might know a different set of forces than these, but I'll leave that to you. So, lift is the upward force, and for aircraft that's created by the wing. So lift is the upward force. We like lift, we like to go up. And unfortunately, weight is the pull of gravity on our aircraft trying to pull us down. So in order to fly, lift has to overcome gravity. Thrust is the force created by the propeller or the jet engine, pulling our aircraft forward through the air. And then we unfortunately have drag that's caused by friction and other things that's trying to hold our aircraft not speeding up, not slowing down, you just set airspeed, going along, then thrust equals drag, lift equals weight. So straight line, constant airspeed. However, if flight condition changes and we accelerate or decelerate, then something is out of balance. So if we shove the throttles forward, get more thrust, that overcomes drag. Now we'll accelerate. Thrust will be greater than drag. If we take our yoke and pull back and maybe add some power too and initiate a climb, and now we're accelerating upward, lift is overcoming weight. Pull our power back, push our yoke forward, begin a descent. That change is now weight is greater than lift. That doesn't mean we drop out of the sky. Weight is just having more effect than what lift has.
If you go back one slide, for that being, you said equalized, right? If the thrust is the same as the drag, how is the aircraft at a constant speed? Shouldn't it be standing still?
If we're standing still, is weight equaling lift? What is greater?
Well, weight. Because if we're standing still on the ground,
Yep.
the weight is, but I don't know, say we're in a helicopter and we're,
Oh no, we didn't talk about fixed.
okay.
Okay, so you're
It just feels like, it doesn't make sense to me that if the thrust is equal to the drag, we shouldn't be able to move forward.
So it's in a set condition. So let's say we're going at 120
So if
knots.
we're going at 120
Yeah.
and that thrust is equaling the drag that is being put forward,
We're in a steady state.
that's
Steady state of
equalized.
moving.
It's like Newton's first law.
Yes. Yes. So if we accelerate to another set state during that acceleration, we're not in balance. But then once we
Equalize.
equalize. So I wasn't going to go here, but I will. So if we initiate a descent, you can go airplane, flying along straight and level now, we nose down. As we nose down, what forces are greater? Yes, gravity. This is a aerobatic pilot. So gravity, weight is overcoming lift. And if I really pull my power back and I slow down as I nose down, which is a good idea, what other forces
Inertia.
of these would be?
Drag.
Yes. So if I'm slowing down as I'm nosing down, then drag is going to be greater than thrust. But let's say I'm at 10,000 feet and I have a good long ways to descend. And after I initiated my descent, now I'm going at 100 knots at a 500 foot per minute descent. MI is thrust again equaling drag and lift equaling weight. It is. Because now I'm not accelerating, I'm not changing direction,
You're not decelerating.
and I'm not decelerating, right. So after a descent or climb is initiated, after that initial change, once I'm set at a set airspeed, set attitude, then I'm balanced again. So you can think of imbalance is any time a change is being made. So initiating descent, initiating climb, or accelerating or decelerating. Can't go backwards, but anyway, you get the idea. So, questions on that? as I'm talking, if I'm get away from my notes, I can say things backwards, so keep me true. I'll keep you awake. Now we get into the fun stuff. All right. So lift. I will preface my presentation with I am held to the ACS textbook way of teaching this. Do I necessarily agree with that? I would say. But physicists to this day still argue and debate about what actually creates lift. So we're going to go over to the two ways that your textbook describes it, because that is what you will be tested on. If you disagree with me, you might not be disagreeing with me. If you disagree with this, totally fine. But you do need to know this style of describing lift for testing purposes. So I'm going to draw a bunch of this out, but first of all, Bernoulli's principle and Newton's third law are the two ways your textbook FAA chooses to describe lift. And we're going to talk about airfoils a whole lot more, but air is coming this way, coming up and over our airfoiling, not all shapes of airfoils. But Bernoulli's principle says because of the curvature of the wing, and I'll go more in depth with this, we have low pressure above, high pressure below. That causes lift to occur. Newton's third law, roughly, and I'll again draw this, is saying as you have this airfoil, and it's curious because there's certain situations you have to use to describe this. But we're at a slightly high angle of attack, talk about what that is. As air comes, it hits this, deflects downward, which it actually doesn't deflect, but just for the sake of the law, hits it, deflects downward. For every action, there's equal and opposite reaction. So because this air is coming down, there's an equal opposite reaction pushing up. Very simply, briefly state. For Bernoulli, you can demonstrate, so people say, well, we don't have actual venturi because this is not a closed tube. It's all open on top, but you can demonstrate it. You take a piece of paper, and what happens if I had another paper on top going here, what would be happening to the velocity of the air that I blow across the top of this paper?
Increasing, be going faster.
Correct, increasing. And what would be happening to my pressure?
Decreasing.
Decreasing. So if that's true, as I blow across this paper, the increasing velocity of decreasing pressure will cause low pressure on top, and it should go up like this. So we'll see if I can do this. Now, is this an accurate description of why it's doing it? But it's doing it. So, I'll show this quickly. You do not have to memorize this for this class or for any maintenance purposes. But I just want you to have an appreciation of, there is a formula for lift, and it has to do with a coefficient of lift, which includes angle of attack, wing shape, times 1/2 rho, which has to do with density, times velocity, how fast you're going, squared, times wing surface area. Super smart people put that all together. But here we go. Here's my feeble attempt to try to describe what's going on. So we've got a this is a cross section. I've put cross hatching lines in there, but I have other stuff to put in here. It could get too messy. So if I were to draw a line from the leading edge, yeah, that looks too bad, to the trailing edge, that is called the chord line. And we already talked about wing chord when we were talking about geometry and wings span versus chord, surface area, and all of that. So then we have our wind coming at our aircraft. So I drew this wing at a bit of an angle. So this aircraft, maybe it's in slow flight, it's angled up, but we're not climbing up, we're just moving forward like this. So if you ever at an air show and saw a military aircraft in high alpha mode, they're going as slow as they can, and they're just like, whoa! Or slow flight in a 172. Not as impressive, but yeah, it's fine. So I'm going to just draw, so we have all the wind coming towards us. So this is demonstrating our relative wind. So this isn't Aunt Martha or Uncle Alfred. This is just relative to your flight condition, how the wing feels as the wind is coming at it. And then we have an angle between the chord line and the relative wind, and that angle is called the angle of attack. So you can think of it as an angle that the wing is attacking the relative wind. So it doesn't like its relatives. So sad. So I'll draw, so as the wind comes towards the wing, there is a point, we're going to talk about that point, where it will either go up over the wing or down and around the wing. And you can see, and we're going to look at some videos of wind tunnels, the air is trying to follow the shape of the wing. With Newton's third law description, they're kind of saying, oh, relative wind comes like this, hits the wing, bounces down, and then the equal and opposite reaction, keeping the, it's not that drastic. But if you take all of this net effect into consideration, you can say, okay, there's going to be a net equal and opposite reaction, equal and opposite reaction to that downward deflection that kind of lines up with Newton's law. Bernoulli's law says, as this comes up and over, it speeds up, so I have higher velocity, and therefore what kind of pressure? Lower pressure, so we have, I'll just put, it's not negative pressure, but lower pressure, and down here is higher pressure. And some have said that, okay, there's part of the air up here that is not disturbed by the wing, so that does create more of a venturi, where this air accelerates and has lower pressure. Take or leave it. Yes?
Why does the velocity increase over top of the wing?
And that's part of what they, and you'll see this on the
Video.
wind tunnel. It does. They'll like pulse smoke, and you'll see this gets back here faster than that does. Which, with Bernoulli's principle, that makes sense, because if it were a venturi, it is speeding up, velocity is increasing because pressure is decreasing. So that does line up with Bernoulli's
Yeah.
principle. There is a theory, there was a theory out there that said there was equal transit time. So it said that when these Papa and Mama air molecules got to the wing, and oh no, they got separated, then Papa and Mama want to get back together again, and so Papa goes faster to meet up with Mama, and then they're the same, but that's not true. And you'll see in the wind tunnels, this one just keeps on going, and that one doesn't catch up with him. So that has been proven to be false, does not work out mathematically, or wind tunnels. With wind tunnels, they also have limitations because they put an airfoil in the tunnel, and they can like change the angle and have fun stuff. But the airfoil is stationary, and they are blowing air at it, so that's going to have different effects than an airfoil moving through still air. So even wind tunnel tests can't be used to prove everything. Alright, so we got low pressure, high pressure, equal and opposite reaction. I believe that shows what I was wanting to show you. Questions. And you may be asked to describe how lift works according to Bernoulli and Newton's third law. So what's a simple way you could say how lift acts with Bernoulli's principle?
Low pressure.
Exactly. High pressure, or low pressure above, high pressure below. That's the basic premise of Bernoulli's principle. And you could say that the air does speed up, velocity increases, pressure decreases, and pressure is greater below the wing. What is a simple way you could describe lift according to Newton's third law? Yes.
Downward deflection of air creates a equal and opposite reaction.
Perfect. Perfect. So that's just what they're looking for. That's just what I'm looking for if I were to ask you that question on, let's say, final. Oh, yeah. Hypothetical. Hypothetical. Any questions? Yes.
So thinking about Newton's law, right? If the wing was flat on the bottom,
Yes.
then there wouldn't be anything to spot.
So that is, and there are different shaped wings. We're going to talk about wings that are symmetrical. And yeah, if our wing is, now, you will end up, the wing is set on the aircraft, or you are flying with a slight, so if you look at an aircraft, it'll be something like that.
Okay.
Like it will be set a little bit like that.
So it's just naturally
But-
cocked upward
correct.
slightly.
Yep.
To make sure that there's.
Yep.
Okay.
But yeah, there are problems if you try to go with just one or the other solely. And when we talk about lift, we also have to talk about drag, because that is the air resistance experienced by the airplane as it moves through the air. And you may have experienced drag yourself if it's a lovely summer day and you have your windows rolled down and you're driving down the road and you put your hand out the car. You have, if you turn your hand this way, you're going to have a lot more air resistance than if you put your hand that way, because you're more streamlined, you have more drag, more resistance with more surface area. So I'm going to show a wind tunnel video. I have a question. Don't answer it yet. Think about it as you watch the video. flying along, it's increasing the angle of attack. So that means the angle between the chord line of the wing and the relative wind is increasing. So it looks something like this, flying straight and level, but I'm increasing my angle of attack. And you may know what's going to happen if we get too high angle of attack. But as angle of attack increases, don't answer, hold it in your hat for now. As angle of attack increases, maintaining same altitude, what is going to happen to lift and what is going to happen to drag? So watch the video and then I will take your answers. And this doesn't have sound in the video. It's a very old video, but some of the old ones are great. Cambridge University. So they have shooting smoke in. Here's our airfoil. You can see air is nicely attached. Here they're doing they'll slow this down. You'll be able to see that the air going over the wing does increase velocity. Right there. Zoom. Bye-bye. Now they're going to do what we just talked about, increase angle of attack. So, straight and level, now we're bringing our nose up. Still straight. And you can see, we're getting some funny stuff going on. Oh, getting turbulent back here. Starting to not have close contact with airflow. Oh my goodness, and we're stalled. Woof. Destroyed lift.
More power.
And all they do is, oh, they'll do it the next one. So same thing, demonstrate again. Flow still attached here, but now, boom, stall happens, no flow. So how do we recover from a stall? We just, oop, bring the nose back down. Bring the wing back. Streamlined with the relative wing. So, what do you think happens to lift as I begin to increase angle of attack? It goes up. How many say lift increases by increase angle of attack? How many say lift starts to decrease? Alright, we got a couple people saying it'll increase and a whole bunch of people not participating. But yes, lift will increase. What about drag? Will drag increase or decrease?
Greatly increase.
It will increase, yes. Increase until our air can no longer stay attached to our airfoil. We lose a lift, and now drag is a big monster, and mushy mush mush down we go. Unless the pilot, recovers. Huh. So, I dropped more hand sanitizer. Do you know paper turns purple with hand sanitizer? So an airfoil, I've been talking about airfoils, is a surface designed to create lift. So an airplane wing is an airfoil. on top, it looks very much like a wing, because it is a wing. It just goes this way. And for you guys, these are portions of helicopter rotors. So we got a composite one here, but this would look very much now, aircraft wing would have more structure inside, but very much like, and actually this one might be from glider, very much like aircraft wing shape. And I'll hold the other one for later. My favorite, well, propellers are one of my favorite. Other favorite, turbofan blade is also an airfoil, because these guys are spinning around super fast, and aerodynamics applies because you can have a compressor blade stall in a turbine engine, that we'll talk about in turbine class. And this one, nice and obvious to see. You can see that looks like an airplane wing. And because these are so cool, I'm going to pass them around. The others I'm going to lose.
That's also from a turbofan.
I'm not sure what this is from. It's very massive. So, yeah, we'll talk in sheet metal class all about the internal structure of a wing, but you just, for now, understand that there's special shapes for an airfoil to create lift. So some of those terms I've been talking about, the curvature, so some are going to be more curved on the bottom, some will be more flat on the bottom. Generally on a wing, especially at 172, you have your more curvature on top. However much, wherever that curve is called, the proper term is called the camber. So camber is the curvature of a surface. We already talked about chord line. Goes from leading edge, which is the forward edge of the wing, straight through to the trailing edge. And then relative wind is the wind coming at our wing. If I was flying along in my airplane, oh wait, let me go to the next one. So then angle of attack, we already talked about, is the angle between the chord line and the relative wind. So if I'm flying same altitude like this, do I have a low or a high angle of attack? High angle of attack. If I am climbing like that, do I have a low or a high angle of attack? Ooh. How many? So I'm going straight up like, well, not straight up, angled up right like that. How many would say I have a low angle of attack? Phew, flight instructor agrees with me. How many say I have a high angle of attack? So it's actually, because it's due to the relative wind, I'm going like this, so my relative wind, or the wind the aircraft feels, is going to be right on the leading edge like that. Because all my airspeed is this way, so my wind, and I can feel it with my hand, is coming right down like that. So it feels like my wind is coming like this. So even though I'm nose up, as long as I'm accelerating, I have a low angle of attack. Now, I pull back my power, and then I just sit like this, and now instead of going up, I'm just going straight. Now it feels like my wind's coming like this, and what kind of angle of attack is that again? Now I'm at a high angle of attack. And yes, I go pretty soon.
Does relative wind take into account like actual wind, like wind conditions?
No. going slow, it can, but it's whatever wind, your airspeed, the wing is feeling that you're at. And then we already talked about leading edge and trailing edge. Questions on that? You have a lovely diagram in your lab. Similar, it's a little different. Similar to this, where you'll be filling on a little. So with an airfoil, there are all types of fun airfoils out there. And here's a trivia question. So standard 172, fairly flat. There's a little bit of curvature, but fairly flat on the bottom, and then we have a nice curve on the top. Super Decathlon is a symmetrical wing. So it's about like this one here. Exact same curve on the top as is on the bottom. Why do you think they designed that wing like that?
So they can do acrobatic stuff?
Exactly. So I got to fly one of these about 3 times. Super fun. And we did some very mild aerobatics in it. But it flies upside down just as well as it flies right side up, because the wing is the same on the top and the bottom. Now, I had to fly at a slightly higher nose up altitude than I was used to in a 172, because some of the stuff we talked about with how lift happens, so that I could get the right airflow over the wing. But then, same thing, when we were upside down, we had to have the bottom and the nose up to get the same effect. So you're flying same attitude, upside down or right side up. And this is just an example of all the different, not all, some of the wing styles they come up with. Then there is what is called a boundary layer. So I talked a little bit about as air comes over the wing, we want that air to stay stuck to the wing and not get turbulent and depart the wing, because then lift goes bye-bye. So that's called the boundary layer, which is a thin layer of air on the surface of the wing. And viscosity helps cause the air to stick to the wing and flow smoothly. So a smooth flow is called laminar flow. So we like laminar flow because that's smooth, gives a super good lift. But there's going to be a transition area somewhere on the wing where your air starts to become turbulent. And the more turbulent you are, well, as you increase angle of attack and are flying like this and increase, you saw in another video, there's a point where that transition area moves forward, turbulence is happening closer and closer until finally drag overcomes lift, down we go. So the stall has nothing to do with the aircraft engine. I don't think I have heard this class refer to stalled engine. I feel like every other year they said, my engine stalled. Like, no, your engine may be quick, but your wing stalls in aviation. But kudos to you guys. Good class. Your wing
We're just better at paralyzing.
no longer And you'll see as they bring the nose up, but they stay in same altitude, they're just going like this, you will see these strings wiggle as the air becomes turbulent. And these are kind of always wiggling because our transition area is about in here somewhere in normal flight. But these will wiggle, and these will wiggle, and these will wiggle, and then they recover, thankfully. So here we go.
better than Bob.
That is about the average. We're almost done.
It was. Since when was he?
Oh, yes. So then when the directions are unreal, so if it makes sense, go ahead and do it.
Maybe I'm thinking of somebody else.
He's like 90. Look at him. He's
Bob
super.
Holland?
Not Bob.
I thought Bob Holland died.
He
Oh,
did. He did. Bob Hoover. Bob Hoover.
Bob Hoover.
You know Bob Hoover.
Oh, yeah.
You gotta love his.
Oh, yes.
videos.
Oh, my word, yeah. Oh, yeah.
He died of old age.
Yes. But the stuff he did is incredible.
We watched videos of his in aerodynamics class.
Oh, that's great.
It's awesome.
Did you do helicopters?
What's that?
Did you do helicopters?
I did. Oh, well, I did a little bit. Like private pilot. Private pilot.
I was asking Bob Hoover.
No, he's more of a plane guy, but he might have flown some helicopters. I just saw his plane stuff. Yeah, it's kind of shared aerodynamics.
I
And,
mean, yeah, aerodynamics.
aerodynamics were shared. Yeah. Well, I was just thinking we were talking about you were talking about the shape of the asymmetrical wings versus.
Yeah.
I say wings, but I was thinking helicopter rotors.
Yeah.
At zero angle of attack, what does it do? You know, when you got like a what's it called? Zero. I can't remember what I'm thinking, but
Oh, yeah.
just the different shapes. What I'm
Yeah.
thinking.
Yeah.
Shapes. It's really cool.
You tell us.
Asymmetrical, asymmetrical.
Are you certified in helicopters?
I have my private.
That's pretty awesome.
I would like to get more training, maybe someday.
Helicopters.
Lord's got me here right now, so.
Helicopters are amazing things, and I want to fly.
If you want to die.
No, not if you want to die, not if you're doing it right.
I mean, honestly,
It's a
not bad.
helicopter. It's
Exactly.
not
It's a helicopter.
As they say about aircraft crashes, you know, there's so many in the air that the statistics are great. You know, you can afford to have one or two here and there.
But then
But
that
like
like
a flight radar
it's like
24. See how
international.
many planes are flying?
Okay, there's a lot of airplane crashes. Only the really bad ones get it on the news.
The airliners.
But then again, there's a lot
I'm
of bad
thinking
stuff that
airliner
gets on the news, and not a lot of good stuff that gets on the news.
They're great.
Yeah.
And really, they are pretty safe. Very safe.
Relatively, it's probably safer than driving.
I know.
Probably.
Like statistically.
Have
Yeah.
you seen the numbers? It's way safer than driving.
Like get whacked out by another driver.
That's true.
It's even in
So,
the driver's
so what you do-
the
what you
driving
do,
course,
right?
it's like flying is safer. See, I told you.
You got a helicopter pad in your backyard, and you got a helicopter pad at work, so you just don't have to drive, you just fly.
Jetpack.
Yes. I like where your head's at.
Oshkosh had a jetpack.
Really?
And one of the Defiance guys came back and showed me a video. I go, here's my ticket to not drive. I'll just get a jetpack and fly everywhere.
It'd be cold like
No, baby, you blink and a bug, your legs burn
Okay,
off.
this is the fine.
that's true. You're like,
Perfect.
oh.
Rusty testy. My legs are marshmallow. Oh no.
You wear
Also, the amount of training that would have to go into being able to just jump to someplace else without,
One thing I'm not a fan of
going.
If everybody had jetpacks, then we just have rules in the sky, we have rules for the road. They could go.
Yeah, and the expense of having the jetpack. I was finally talked out of getting a jetpack, sort of.
Don't give it up.
Oh, who made it?
I just want an airplane that can take off in like 10 feet and land in 10 feet so I can just fly it everywhere. Oh, gyrocopter.
Yes.
I don't want
They're scary.
These are messed up. I want an airplane. Good
It's up for sure.
airplane.
It sort of works like, it's like low speed. It's like a low speed.
I saw, where was, I was at,
I don't trust it.
guy came in and he was like, oh,
A little bit safer than a helicopter because it'll fly itself. It has a wing technically. The gyrocopter.
Yeah.
It's acting as a wing.
But then the regulations for it are so
But it's
vague.
right.
It just
I hate when I come into the airport and they're like, gyrocopter, like, oh no, where are you? What are you not doing? How are you gonna get in my way? like aircraft 172 wings. And then it's now it's a little boo-booed in the back, but this is more of a symmetrical airfoil. So you can see this is same top and bottom. This is different top and bottom. So this is a example minus the boo-boo of what a symmetrical looks like. So we talked about the boundary layer. So someone would simply describe kind of what that means and what happens when things go bad.
It's where it transitions to the turbulent air.
Yep. So we got smooth laminar flow and then transition area where it's turbulent, and as we increase angle of attack, turbulent area moves up. So we want to help that boundary layer. We want to keep that attached and have them be good friends. So ways to help the boundary layer. First of all, very simple thing that every one of you can always do is keep the wing clean and smooth, which you'll do if you ever have to do repair. You're making sure you have a smooth, flush repair. But a clean wing versus even frost can be really bad, because now it's making the air go all bouncy, bouncy, turbulent. But other things we can do is leading edge slots. So what this does, here's our normal wing, air splits, this goes up, bouncy, bouncy. But by having a slot, we're drawing in more of the air that normally would just go under the wing. And it might be hard to tell, but can you tell what that looks like that we talked about yesterday, in case help demonstrate? It is a venturi. So what's happening to our pressure? It is decreasing. So that's drawing that right up and then sucking it down to the wing. So that's slots. Then you'll see on some of our aircraft we have vortex generators. So that's these little V's they look like on top. So they're kind of like short airfoils. They'll always be in pairs along the wing's upper surface. And what they do, they help pull the high energy air slightly above the wing down onto the wing and keep that airflow attached. Something that is not very common, but your book does talk about it, is small suction holes. So these can be on gliders, and they'll take tubing or piping from below the wing, pipe it up on top of the wing to take that high pressure, and then kind of like force it out so it's blowing along the wing and helping to draw down the air against the wing. There have been on some military high-speed jets experimentation with some like using a compressor, tubes, and valves to actually blow high pressure air over the wing, and then a hole to draw air through, like a whole system of airflow. None of it really, the cost, the expense of manufacturing it and maintaining it was not, it was way too much compared to the effect that it had. It did help, but not enough. Yeah.
So is the only difference between the section holes and the leading edge slots where the intake is coming from?
So that is a difference. Yeah, the leading edge slots, you just see them out on out on the front of the wing, very obvious, and they're just giving this slot for the air to go through. It's coming out the wing, normally it would go under, just going up and over.
Gotcha.
Where the holes would be pretty small, and they would just be like on top of the wing, kind of the length of the wing back towards how far back they want that. And then it would have ducting on a glider from under the wing up, and they would have lots of ducts probably going up through. coming off your wingtip. And if you fly an airplane through clouds, you can see really cool effect of wingtip vortices. And these can be super dangerous to pilots from large aircraft. Then you get wake turbulence, which, so, yes, wingtip vortices are dangerous. Now, we move into the really fun stuff. So, this has been notoriously confusing for people. So I hope to teach it straightforward, so it's not too confusing. But I'm gonna quiz you so that hopefully you get it set in your brains. And the more you understand this and have it memorized in this class, the better off you'll be when you get to Ryan's flight controls class, because he will also be teaching this, reinforcing it, and testing you on it. So what I'm talking about is the axes of an aircraft, the movement about those axes, and the type of stability. So first, we're just going to start with each axis. So this is my airplane with either really tiny wings or else no wings. But the first one they have here is the longitudinal axis. So that goes, if I spear this aircraft from nose through tail, the long way of the aircraft, that is a longitudinal axis. Longitudinal from nose to tail. And then my lateral axis goes from wingtip to wingtip. So if I spear it through the wing, that's lateral axis. If I go right between the passenger pilot seat, I'm not spearing any person, that is my vertical axis. So vertical axis from top to bottom, lateral axis, wingtip to wingtip, longitudinal axis, nose to tail. Questions on that? Now it gets tricky. So, with my longitudinal axis, move this airplane for a little bit. So, longitudinal from nose to tail. If I move around or about that axis, what flight controls are making that movement? Ailerons, because these guys make me roll. So movement about the longitudinal axis, well, that's a good roll. It's called roll, controlled by the ailerons. So we talk about axis and instability about those axes. So stability about the longitudinal axis is lateral stability. So if you think kind of opposite, around the longitudinal axis, I am laterally stable, or not stable. Then, kind of the opposite, my elevator, you should go back here, oh, he only has one, is going to control my pitch Stability is that. Directional. Very good. Very good. This guy's confused. He doesn't know where he's going.
Too long.
Any questions on that? I'll be putting this PowerPoint up, so I encourage you to kind of memorize this chart, be able, if anybody asks you one part of that, you'll be able to whip out the rest. Not today, but by Ryan's class. Another aspect that's very important to talk about, there's talked about briefly in this class, a lot more in weight and balance, is the center of gravity of an aircraft, or you could say where all the weight is concentrated, or if I suspended this from a string, where would it balance? So this aircraft actually has a really far aft center of gravity because there. It's like balancing. That's interesting. But in design and where you place weight, you need your center of gravity, or where all the weight is concentrated, where gravity is pulling down. You need that forward of the center of lift, which is where all the lift forces are considered theoretically concentrated, and we're pulling up on the airplane. Why do you think that is? What other aspect is happening back here, do you think? Because if we just had those two forces, if I have center of gravity here pulling down, center of lift here pulling up, we're not doing so hot. So what do you think is happening on an airfoil? Yes. So our elevators are actually designed to have a downward force. So air is flowing, giving a downward force on the elevator, so that we have center of gravity, center of lift, downward force, and it all equals out. So to help, yes.
Why don't they just put the wings more forward?
To get your center of lift closer to center of gravity,
Yes.
then you'd be more, we're going to talk about that in weight balance, more unstable. Because the closer the center of gravity and center of lift are, the more unstable you are. The wider apart, you have greater arms, so you're much more stable. So to help with stability, there's a number of different things, but one of the things, and you can see this on any of our aircraft, Cherokee might be more obvious, there is dihedral. So that's kind of the angle that the wings are attached, looking from the front, to the aircraft as compared to the flat surface. So here, if we have flat ground, we have an angle of dihedral because our wings are up. And there's a lot of physics and stuff that could go into, we won't, but that the way that lift acts, as this wing comes down, that's changing angle of attack, so that lift is actually increasing on the downwing side to bring that back up and stabilize itself out. And you'll learn a whole bunch more about dihedral in Ryan's class. So someone had mentioned, let's go over parts of an aircraft very quickly. So okay, wing, hopefully all know wing. And what is out here at the tip to do what motion? Ailerons for roll. And back here, this little guy moving back and forth, rudder. And that's for what motion? Yaw. And then these are supposed to move together. This is what? So this is elevator, because what is this portion here? It is stationary. Anyone know what that's actually called? Horizontal stabilizer. So it stabilizes, it does not move. It's like a 172, it's just in place, will not budge. Your elevators are what are controlling your, what is this motion? Pitch. Now, you can have, oh, and what is this immovable portion called?
Vertical stabilizer.
Vertical stabilizer. So, you can have a situation where you do have this whole horizontal surface move and deflect. And that is called a stabilator because it's the stabilizer and elevator combined in one. So, stabilator, the whole thing moves, and you can have the whole downward deflection, whole upward deflection, but it has to have an anti-servo tab on the back. And as the stabilator moves up, the anti-servo tab moves in the same direction. And its purpose is to increase control feel to prevent the pilot from over-controlling aircraft. So it's trying to bring this back into a streamlined position. So it's, yeah, increasing control feel so you're not yanking that aircraft around. Another unique surface is a rudder vader. So what two normal surfaces do you think this combines? Yes, rudder, elevator, stabilizers. So rudder vader, and you can see ours on our, well, the remains of it on our bonanza. But it is rudder, elevator combined. And you don't have to memorize this, but both down, pitch the aircraft down, both up, pitches up. The right rudder, then you go right, left rudder, vader, go left. That's how it's controlled. Yeah.
Can you just clarify the anti-servo tab? That's just so that you don't have to move the whole thing that would cause more stress, or?
No, it's just to increase, so as you pull back or push front, so the air's coming over, it's deflecting air onto that, so that if it didn't do that, it's making it a little bit harder to pull back or push front because it's deflecting more air down. So that keeps pilots from just shoving it too fast, too far if it was easy to move. So it's helping prevent over-control by the pilot.
Why not just make the control heavier through other methods like those stronger cables?
Probably because this is simpler and cheaper, I'm thinking.
Train your pilots to not over. Alright, so quick review before we dive into some other things. So these are called primary flight controls, what we already went over. So ailerons, rudder, elevator, primary flight controls. Examples of primary flight controls. So now we're going to talk about secondary flight controls. Secondary flight controls modify the effects of primary flight controls and do not of themselves cause rotation of the aircraft on any of the axes. So the first one I'm going to talk about is trim tabs. So here is our whole aileron, and in the aileron can be an aileron trim. Within our whole rudder can be rudder trim, and within our whole elevator can be elevator or pitch trim. And you'll see different variations on different aircraft. One little tidbit. So anyone know
172s have also. It's just a little piece of metal that you can bend because aircraft have left turning tendencies, so they bend it to help turn the aircraft to the right. But it's set because you have a set engine, you have, yeah, average way that it operates. Oh, that actually brings up another story. I'll just tell a story. So, at my flight school in Pennsylvania, one day I was flying. Let me think this how it was. Yes. So I forget which way it was for sure, but anyway, it took me a while to get landings down good. So finally, I was nailing landings every time. I was like, okay, I've got this. And I come in, I flew like about once a week or once every other week. And I came in for a landing, and I could not maintain centerline. And, no. I was struggling again, because we were flying down the runway. We were not landing, we were just like flying low, and I could not stay on the centerline. I just kept veering off, and I get back and veering off and get back, veer off. And I was like, man, this is frustrating. I had it down. And we worked at it. And so I was like, okay, I'll come in next week. And he's like, yeah, I know, you didn't do very good. I was like, I know. So then he emailed me a day later. He's like, yeah, thinking about it. This student right before you in the airplane had the same problem. And so he looked at the airplane, and here the mechanics had worked on it, and the trim tab had got bent the wrong way.
Refund.
I was not happy. But I was relieved it wasn't totally my fault. I was like, oh. Anyway, I'm telling too many stories. Okay.
There's no such thing.
Our Cessna 206 has a movable rudder trim. So I'll show you a picture, a wheel to change pitch, a wheel to change rudder. Here's a tidbit. On a 182 and a 210 and a 172. If you ever see aileron trim, or they slap on a piece of metal you can bend like the rudder, that airplane is messed up. Because they have the wings somehow not rigged correctly, and they're trying to compensate with slapping on aileron trim. So if you ever go to buy an aircraft, watch for that. Okay. So here's a lovely 172, our trim tab that has cables that go up in the cockpit to this trim wheel. And on the 172, it's in the console between the seats. And you move the wheel down like this. Now, this could be confusing. Moving the wheel down like that gives you nose up trim. Purpose of trim tabs is to relieve control pressure for the pilot. So once you have your yoke set or stick to where you want it, you're in flight, you don't want to be hauling back the whole time or pushing forward or whatever you need. You want to trim off the pressure. So this will deflect air to make the elevator more effective. So then you trim off, and now you can fly with just 2 fingers and not have extra pressure. So you set your attitude, trim off your pressure to relieve pilot workload. Pilots don't like to work, apparently. So moving this wheel down gives nose up trim. So the way I think of it when I was trying to figure this out is I'm grabbing the nose and pulling the nose up, if that helps you. So moving the wheel down gives you nose up trim. Moving the wheel up gives you nose down trim. So if you think you're grabbing the poor airplane by the nose and shoving it down or pulling it up, that might help. And how it works is, as we trim nose up, our deflecting the air, helping to keep the elevator down. So it's very, very important when you as a mechanic are rigging the flight controls that when you move the nose wheel up, the trim tab flips up. And make sure it's opposite of what the elevator is doing, because there have been incidents where it's rigged incorrectly and the pilot crashes because they're trying to trim what's going the wrong way, they lose control. So this is something very important. After you rig it, step away, get a cup of coffee, come back, check it, and get another buddy to come double check you. Super important.
Christina,
Yeah.
Starting to understand the difference between the trim and then the anti-servo tab.
Yes. And that's an excellent question, because that's what I'm addressing next. Because that's a very good thing to realize. So the thing with, so here's the anti-servo tab. So the anti-servo tab is going to be on a stabilator. That this whole thing is, whole surface is moving, and it moves with it. It moves automatically. So there's no adjusting a trim wheel, it just moves automatically with that control. Where the trim is going to be part of the elevator, and the pilot uses the trim to help him out to take off control pressures.
So the anti-servo is making it harder, or so you can feel the more resistance, and then the trim pad is so you feel less.
Yes, yes, to take off the control pressure, because you're set there, you're not using the trim when you're moving the control, but after you moved it, you're set where you want to go, and you move the trim. Yes.
And those be the same tab, or are those always two different
It'll be
surfaces on the elevator?
So if it's an elevator, it will have, because the elevator surface is smaller, so you don't need the anti-servo tab.
Oh, right.
So elevator would just have a trim, and then the anti-servo tab would be on the
It's only on a stabilizer.
stabulator. Yes.
But stabilators also have the trim tab?
I believe they would. Yeah, I'm sure they do. Yep. And so, yes, you have the anti-servo tab. Then we have another one thrown in the mix, which is a balance tab. So this one is for very heavy flight controls, so like airliners that are still a cable and not fly-by-wire. So this one automatically moves with the control surface movement in the opposite direction. So the anti-servo, this is going up, that goes up. Balance tab, if this goes up, the balance tab goes down to help move that control surface. And yes, it'll be opposite the direction of the control surface. So an anti-servo is sometimes called an anti-balance tab. You may hear that. So these you can think of as opposite. Another device is lift modifying devices. So if we design an aircraft wing to give us a ton of lift at slow airspeeds, we'd be super inefficient at high airspeeds. So that's why they develop flaps, and not all aircraft have them, but they develop flaps so that you can have a decent cruising speed, but then you have the ability to have a lot of lift so you can fly slower. And to show you the advantage of flaps, descent angle, but you're not just plummeting towards Earth. You have the flaps helping slow you down, so you can clear obstacles as necessary. So this is a no flaps approach, which you for sure, I do this into Ionia, especially if it's windy. But we have a super flat descent angle. And then half flaps, full flaps, you can just dump that in over the trees and land.
It's a happy tree.
I hate it when they do that. They put a tree in the middle of that.
So inconsiderate.
Inconvenient.
Why does it have to be in the way like that, man?
I don't know. So, what happened to camber? Who remembers what camber is? It is the curvature of the wing. So, what is happening to camber of the wing? Increasing or decreasing? Increasing. So when we add flaps, we're increasing the camber, which is then increasing lift capabilities. If lift is increasing, what else is increasing? Drag. So sad. Alright, here is one of my other favorite aircraft, the Heliocourier. How many of you have seen this fly? Sweet. They don't fly it as much anymore, but they try to still do demos sometimes. So Jars is the one that still flies Heliocouriers, and then there's some individuals out there. But another flight, secondary flight help is a slat. So a slat is different from a slot. So someone can give me a definition for a slot, or what its purpose is for. Oh my.
It's to keep the airflow over the top.
Perfect. So to help keep that laminar airflow. So this helps with that. It also, what's it doing to camber? Increasing it with the front, just extending that whole wing so we can have a whole lot more lift going on. But slats are retractable. So they can go in, smooth and streamlined when you're at higher speeds. But then as you slow down on the Heliocourier, they are pushed in just with airspeed. So as you go faster, they push back in. And then as you slow down, they plop out. And the inboard slats will deploy about 43 knots. The outboard slats at about 39 knots. With the slats deployed, full flaps, stall speed is 24 knots. Wild. It's so cool. The wing is massive. When they have flaps down, slats out, it's just a incredibly massive wing. And it can just like pretty much looks like it just hangs.
Then why don't they use it more?
Well, it had a geared engine, which was a monster maintained.
Don't they have the STC to modify the engine?
I don't know if they do or not. Okay, so then sometimes your wing tries to run away, so you have to give it a fence. Not true. But these are wing fences. Has anyone noticed these on any of our aircraft? And which one?
Beach jet?
Well. Yes. Yeah. It is on the beach jet and which other of our aircraft? This one's a little harder to see because it's on the top of the highway. Oh, thinking. A 210. Yep, it's on our Cessna 210. So, what the purpose of a wing fence is to obstruct span-wise airflow to help this area of the wing to stall first. We're going to talk about another device that does that, but why, somebody besides a pilot, why do you think we would want this area to stall signal from your stall horn and the buffet from the inner part of the wing, so you can recover from the stall before things go bad. Another component is a stall strip. So it's just a triangular piece of metal. And have you seen this on any of our aircraft? Yep. Yep. And I'll let you take a look after I'm done lecture. If you need to get up and walk after lecture, you can go look, see what aircraft has stall strips. But the stagnation point is a point where the air is either going up and around or down and around the wing. And that stagnation point moves as the wing increases in angle of attack. That stagnation point starts to move, which then is causing more turbulence. So they put this sharp pointy thing on to encourage that point to have a, here, this is a little better. So that sharp pointy thing makes the air become turbulent sooner. Same reason we want our inner portion of our wing to stall first before the outer portion. So on aircraft where the whole wing would tend to stall at the same time, we put a stall strip on the inboard portion of the wing. Okay, you all are having a rough Friday afternoon. Take a break. Come back at 25.
No, we're describing a story.
Oh, okay. I didn't want to ignore you.
Sorry.
Oh, you can throw. That wasn't bad, man. Dude, we gotta get, that wasn't, we gotta get a bully. That was 500.
After Sunday afternoon, talking lunch, nobody was at him anywhere near, so we talked for so long.
What is it for? Or is that just because it's at the end?
Oh, right, it's the wing tip, right?
Yeah, but wing tip of what?
He's such a troll, bro. Oh, man,
Christina, where did you take lessons out of?
Lancaster Aerodynamics.
Okay.
Which, it was a really good school. Like, their chief flight instructor is great. I think I just ended up, he didn't stay there long after I.
It must have been like organizational things.
Yes. Yes. Because, yeah, other people, like, have gotten really good.
Yeah.
I just got a
Yeah, that's funny. It's like, I just took a few lessons out of York, and
Oh, yes.
I had some similar experience.
Oh, no.
It was like, I don't know what it was, you know, I was just like, let's do this, man.
Yes.
It's the same thing.
Yes.
Yeah, that's cool. I'm also curious, what's your ideas on, like, trying to be like this? Because you were like, I don't agree with this.
Right. Well, it's
too, like Bernoulli's like, it doesn't quite make sense.
Yeah,
Okay.
yeah.
I was just
Well,
curious.
with the symmetrical wing, it doesn't make sense.
Yeah, especially with the symmetrical.
Well,
how-
you do
how
have
could
to
it-
fly at it with a wing.
Right.
Yeah, but Bernoulli's principle
So then it,
couldn't be
shouldn't apply at all.
Right.
because it's
Symmetrical wing.
accelerating on
because
equally on
it's,
each
yes,
side.
Right.
yes. And that's, yeah, that's probably like, this breaks down. Like, this isn't,
Yeah, that's
it's more-
really curious.
it's more that I'm not, if somebody said, oh, it's one way, like, no, but I'm not sure
Now,
how, what the way is.
On symmetrical wings, I thought I've seen it somewhere where on symmetrical wings, they'll be symmetrical somewhere and then the camber will change, like when you get top, sort of toward the outer edge. So like they'll be symmetrical maybe more towards the root and then more towards the edge, they're more
It
normal.
can,
I don't, that doesn't explain it either, I've just heard that.
I
but-
know.
It looks like it's surprisingly PP6 safe from
So,
AOPA, so I think.
I wonder, cause that's, what's a bigger PP6, is it dash 46? I forget what's in the Kodiak. Well, it probably ends up, the Kodiak could be bigger,
I feel like redwood trees.
Oh,
and has bigger payload.
you're doing good. You're doing good.
King is really 610.
I know.
And just think what it can do at sea level. In slow flight, I didn't find slow flight on it. They probably weren't allowed to go that slow.
Right, I do wonder how that.
Maybe if I poke around more. I didn't ask them like but they didn't have the turbo either. I did ask with them. I did ask them. But that was so much fun. That was a fun air show. Just, that was my first year in the missions tech section. We couldn't bring the DC-3 because it had just had so much maintenance left and we were low on staff and we couldn't do that. So we just were at the booth, so it was my first time at the booth.
Oh,
And
that's so
the first time at the missions tent, because usually we're not in the missions because DC-3's big and they're warbirds.
yeah.
So it's really cool getting to talk to everybody else and it's wow. It's one of those things, wow. It's not just us.
Right, yes.
We're not the only ones.
Yes.
And now I get to talk to everybody and wow, this is so cool. And the IAMA conference was really cool too because it's like, who does this? And wow, you understand what I'm talking about.
Right.
This is like nice.
It's like my people.
I got invited to go to, not really a missions conference, it was something very interesting, just special for missionaries to Haiti. It was a really small group that I just happened to be in the right place at the right time. And I was invited to come. I was supposed to get quilting with my Aunt Karen. But we went to drop food off the place from a food bank and they were meeting. And I said, you're supposed to be something from Haiti. Well, sort of, yeah. You want to come in?
Oh,
So, but there we went, it was about trauma and how to handle the trauma with Haiti and
Oh, yeah.
your experiences there.
I've been trying to
This is so cool. It's because you're with a bunch of the same missionaries from different parts, but it's one of those things where you can talk and not have to worry about how do I explain this the right way.
you had the same experience.
And they're like drawing out, and you know I don't draw out of Haiti. I've seen so many missionaries coming out, and it's like, yeah, it's really sad. And the people are saying, yeah, you're home.
You don't want to be there.
That's my home.
Yes.
This is not good, and then you're trying to figure out how to fit in with the regular civilization.
Yeah.
And that part was very interesting too, because other than a fight, it's really kind of, people don't consider us missions because we're in the States, and we're not really normal. So they're a funny color, green.
Yes. Yup.
And then in the fights, were a really funny color, green. Because we're just our operation, you see both sides, and you're not,
Yes.
you're fully one, and you're fully the other, but you're not really fully the other, but you're fully one, but it's really
Yeah.
complicated. But it was really fun going to that. And that was so much good information.
reaching the end of this lecture, so you can rest easy. I know. I love talking about aerodynamics, but you might not love listening to it. Okay. So we talked about wingtip vortices, which, why do they happen?
Because the high pressure on the bottom wants to meet up with the low pressure.
Yep, yep. Over a wing, low pressure and high pressure want to equal out, so they get out to the end and go, yeehaw, this is much more fun. Like that. So, we can put things called winglets on the end of our wings to help control that departure of low and high pressure air. And we still have little baby vortices, but they're little baby ones. They're not going to be as big of a negative effect as the large ones. So that is why you'll see wingtip or winglets. Not only do they help with prevent turbulence, the little guys flying behind them, but it helps increase lift and decrease drag because you're shedding that off with less turbulence going on. And we are going to talk very, very briefly on high-speed aerodynamics. We'll talk a lot more in other classes, but the biggest thing you need to know is what happens with velocity and pressure. So, if this was not supersonic, if this was just normal subsonic airflow through, what is this duct called? A venturi, because it narrows, and we have convergent, divergent ducts. What kind of duct is it when it narrows down? Converging. If you think of traffic having to converge, it's bad because they all are trying to squish together. And then what is it called when our duct widens out? Divergent. You'll be, I was going to say quizzed on that, not quizzed, you'll be labbed on it. So what is happening to velocity as our duct narrows down? Increases, and then what happens to velocity as it widens out? Decreases. What happens to pressure as velocity is increasing? Pressure is decreasing. What is happening to pressure as velocity is decreasing? Pressure is increasing. Well, guess what? When we go supersonic, everything flip-flops. Because, here's a wild thing. As air, well, after it becomes supersonic, once it is supersonic, it acts like a compressible fluid, which is weird. So it behaves very differently when flowing at supersonic velocity. So this is why airplanes, supersonic capable airplanes, have to have different shaped wings or wings that can change shape. So in a converging duct for supersonic air, if you memorize subsonic airflow, you just think opposite for supersonic. So velocity actually slows down, pressure increases, density increases because it's kind of wackadoodle. And then as it widens out, now velocity is speeding up, pressure's decreasing, density decreases. So just be familiar with that. We're going to talk a whole lot about that in turbine class and exhaust systems and intakes, because you have to design intakes if you have a supersonic aircraft to slow that air down before it reaches your turbine where you'll be shedding blades right and left. And then exhaust, we design it to go supersonic so you can gain more thrust. We'll talk about that in those classes. Just for now, make sure you memorize subsonic airflow through a venturi, and then you can think of the opposite for supersonic. Now, we are going to speed through rotor wing a diagram similar to this, make sure you know these parts. So, fuselage, main body of our flying machine, just like an aircraft fuselage. Then we got landing gear or landing skids, and our pylon or the mast comes up to our main rotor hub assembly, going out to our main rotor blades, and hopefully it's not like our poor little home built that does have a power plant in it. This looks maybe Allison 250 turbine. And connected to the power plant, you need a transmission to go up to your rotor hub, make that spin. And we do have stabilizers back here on the tail boom. And then there'll be a tail skid and tail rotor. There are other designs. Some don't actually have a rotor, or it may be enclosed. Ryan will talk all about those in rotor wing aircraft class. You do need to know the 3 classifications of main rotor systems. And they're classified on how they move in relation to the hub. So, the rigid system means the blades are, so we'll pretend this is a helicopter rotor instead of a beautiful propeller. All that a rigid rotor blade can do is change pitch. That's it. So it can change pitch as it needs, or blade angle might be more appropriate. So it can change blade angle as needed. When we talk about a semi-rigid system, these blades can change blade angle, but they can also do what is called flap. So they can go up and down like that. Whoa. So one blade goes down, other blade rises, or so flapping. And the last one, fully articulated, means it can do all the things. So it can change blade angle. It can flap. And it can move fore and aft. So fore and aft, flap, blade angle. Yes.
Why is it flap? Why is it flapping again?
So we will talk about that in just 1 minute.
I was picking on it.
Oh, you are? Because actually we'll talk about it.
No, I know, I don't wanna get into those weeds. It's deep, so.
It is. It is.
Yeah.
And the next thing to talk about is the flight controls, which we'll talk about like the whole thing moving like that. But yes, we could get very deep very fast. So then, and I'll ask for mercy from the helicopter guys like I asked for mercy from my flight instructor. So flight controls, again, we're keeping this very simple. And you can go out to our rotorway and play with the controls. But, so normally, helicopter pilot sits in the right side. Is that normal? Right side?
Yeah, it's the opposite to normal.
Yes. So your controls would be here. So
It'll work.
the first one I'm going to talk about is the collective. So that's on the side here. And, or they call it the pitch stick. I don't know if that's something you'll collective, and that is going to control your vertical flight. So as you pull up on the collective, go up, down on the collective, you go down, and when the collective pitch control lever is raised, this is counterweighted, there we go, is raised, the blade angle of all the rotor blades increases uniformly. So they're increasing to give you a greater angle of attack, which is giving you more lift. So you go whoop, up, and opposite to go whoop, down. The cyclic, which is in the center, you can use to go, it says that you can think of it as the yoke in the airplane, but it is your directional control. So right, you're gonna go right, left to the left, forward, back, in crazy circles. So the cyclic changes the pitch of the blades individually, so you can have more lift on one side or less on the other side, or it'll tilt the whole plane of rotation of your, whoa, now I'm gonna get busy, of your rotor head. So it's like that, I can change it like that, so it's rotating like that to help you go off in whatever direction you please. And then, these are not rudder pedals, they are anti-torque pedals, because what do you think is happening with this whole massive beast spinning around on top of you? I'm trying to, spin you around. Torque. So we got massive torque, which is why we need the tail rotor or some system to counteract that, and you're controlling that with your anti-torque pedals to keep you going straight and not spinning in circles. My helicopter guys have anything to add? Keeping it simple.
No, it's fine.
Thank you.
What RPM did you get your blades spinning at? I'm just curious how fast they actually spin, just on normal, not
Normal RPM of our,
Normal RP, it depends on the helicopter. It really does, the size of blades, everything.
Weight,
that makes sense.
we don't know.
Kind of like a prop on a plane. So we're like,
Problem.
It's slow compared to a prop.
right, yeah,
There is a ratio, it just depends on like, you know, looking at POH.
Yeah.
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 Oh, cool. I think you're first.
I'm just curious if that system, and I mean, yes, it's torquing it, and it wants to spin it. If that system had zero friction, and would it still want to? Or is that getting?
You still have torque happening.
Okay.
I mean, yeah, if you get up to a certain speed, your horizontal stabilizer will take the job of the torque pedal, you know, the actual tail rotor. But once you get below a certain speed, the torque will start taking over again. Because there's, you know, situations where your tail rotor stops working,
Yes.
and you gotta figure out how to land through that.
Question.
Do the anti-torque pedals control the pitch or the speed of the tail rotor?
Ooh.
It's just the pitch of the blades.
So yeah, and the so it's just not this, because that would be
It's a set speed, but it's connected to the engine directly.
right. So
It's a
that's
ratio
all
of the
geared.
main rotor.
Yeah. Thanks, helicopter guys.
There's a lot of pieces that have to work.
Yes.
Yeah, so like on
Yes.
these helicopters, the engines have drive shafts that go to the aft
Right.
and the head, and so it's all calculated between the two to balance them.
And yeah, we actually get into that teeny tiny bit in turbine class, so we talk about turbines on airplanes and helicopters. But then yeah, Ryan will get real deep into it in his class. Yeah.
Can you restate there's the rigid rotor blades?
Yes.
And then there's, sorry, I kinda.
Yes. So rigid, they only change blade angle. Semi-rigid, they wave hello. Change blade angle. Fully articulated, they change blade angle, wave hello.
stresses, but the rigid is, they take in all the stress because of their nature of what they're, like a composite.
Right.
Yeah.
Yes.
It's really interesting because they're really strong.
So that's cool.
How do you change pitch in a rigid?
How do you change pitch in the, so that would be, depending what you're doing, whether you're raising the collective to increase all the pitch the same.
No, I'm talking about like pitch of the like pointing the nose.
Oh, like
this
the,
or
ooh,
like
here we
that.
go, like, whoop.
Yeah.
So that would be collective down, is that right?
Yeah, so
Or
the head actually pivots.
cyclic. Yeah.
But
Cyclic.
if it's rigid, then what's the force that makes it,
Changing, I believe, changing,
It's like rotor
This-
tip back plane,
yes.
changing, like
Yes.
you said, it changes all
So
the
your
times
whole, your rotor head.
instead of leaning forward.
Yeah.
So that, the PC link, with the red tape on it,
Yeah.
yeah, that one, the rigid, that's a PC link. It'll literally change the pitch of your blades, and the whole head has like a cylinder on the bottom that actually pivots like this inside the helicopter.
so with rigids, it can still pivot?
Yes.
Okay.
Yeah.
Very good question. Any other? So, we have concluded, and that's good time, the physics lectures.
Wait a minute, I spent 45 minutes in the labs.
Is your head spinning yet?
Oh, oh man.
Yeah.
How do you manage that?
That looks like a rat.
How do you manage that? I would
All right.
guess just a
What's
roll.
that?
I'm going to open up
I think that's right.
your very last lab,
We're getting
and
there.
we'll go over it.
We'll get there. Good job, Christina.
Alright, if you go into the school, there you go. And I just opened up lab 7, which is the last lab for this class. If you go into lab 7, well, isn't that fun? Most of the questions are going to be right out of your textbook. If not, it will say otherwise. I want to point out question 13 to all of you. Now, the guy that designed these labs, really appreciate him. He put tons of work, tons of thought into these. But the one problem we had, so this is a whole cool image he placed in here. It can't be edited. All this is really good stuff to figure out, okay, what is high velocity, low pressure, all really good stuff. But I'm going to give you a freebie. So, back here, it says this is traveling a longer distance. This is traveling a shorter distance. Which, okay, yeah. Is that relevant to how we understood lift today?
Not really.
No. It kind of harkens back to that whole, Papa molecules want to meet up at the back. And yeah, so that's not really relevant. But we couldn't undo those little blocks that just put longer distance, shorter distance. But the rest are very applicable. So yeah, the rest of the time is for lab time. You will, my plan most of Monday will be for the final. It's a fairly, I forget how many questions, it's fairly extensive. It is open book, so if you want to take all 4 hours, you can. But you will, I don't expect, maybe 2 hours, maybe, to take the final. So you will also have lab time Monday. I might come up with some fun things, but I want you to have lab time, plenty of time for the final. Nope. The final will be kind of like a quiz. A lot of short answer. Because it's open book, it we're not doing prepware. That's like, find the information. Yeah,
Formulas and stuff.
yeah, yeah. If you have any work from a previous class of mine, if you finish up physics, make sure you're working on that. Also, I think Angie put in your boxes, if anybody has any failed labs, make sure you redo those so you get passing grade. You do need a passing grade for every lab, quiz, and final.